Okay, good morning, everybody. Um, yeah, we're going to try to get some questions here regarding area now today with polar curves. And let's see if we could get this up and running here for you guys. All right, now let's go to the iPad. All right, there we go. Okay, so we do have some things to look at. So let's go to Word. And we don't want that. We want to go to Math 262. And you got the calculus of polar curves. So we have all these things we went with briefly yesterday. And now I want to talk about this area under the curve. This is where we want to focus today. Okay, so we're going to look at this. This is something that's also in your book. You want to determine the area bounded between lines here. So let me see. I might have to go back for a second. Cancel there. Let's try something. All right. It's supposed to be okay. There we go. And so let's remember here that a line is given by theta being a constant. So that's in some sense your lower bound. And I call that constant alpha. Here's another line, and theta is a constant, and we call this constant beta. And so what we're trying to find, which is completely analogous to area under a curve between vertical lines. These lines are not necessarily vertical, but they do go through the pole. They go through the origin here. Okay. And then in blue, as you guys can see, we have a curve. R is f of theta. And in blue here, which I'm going to shade now red, this is the area that you're looking for. Now, I have a proof for you, or I have really an argument. The formal proof is in your book. So here's kind of essentially how this goes again. We want to partition our interval or theta interval into n subintervals. And this is the partition here. And of course, we have a delta theta, meaning that's the difference. That's the small partition. So you're partitioning the interval theta over AB or alpha beta here into n subintervals like always here. So these are the kind of things that we do, right? Partition into n subintervals, the theta. And so what we have here will be a picture of what we call a sector. So we're going to approximate this with a sector. And this is the sector here. So there's our sector. Area of a sector, though, is 1/2 r squared theta, where this is the radius. Remember, a sector comes from a circle. It's a portion of a circle. It's like a pie or a slice of pizza. And we define AI for all those areas, the I areas from 1 to n, to be 1/2 r squared. And this is a subscript down here. Should be Ri, right? Delta theta. So we're going to add these areas. That's what a summation is, which is 1/2. And remember, R is actually f of theta. So if you have Ri, you get theta I. And this is where this portion comes from. It's really r squared. Okay, so you have that there. And we add these values, these n subintervals, and as n goes to infinity, this is a limit, this is a Riemann sum, this is now exact. And this is the integral. So this is the formula we're going to be using today. Okay, it's 1/2 r squared d theta. That's kind of how I remember this. And of course, r is a function of theta. And this is going to give us how to find area over an interval where the angle is going to be between alpha and beta. Okay, so here's where we're starting. And then you have, I have a proof here for you if you want area between two curves now. Notice I have a second curve. Here's my first curve. Here's my second curve. Just to kind of remark about that. Here's the proof that the area of the first curve minus area of the second curve is given by these two formulas. And again, there's a difference here. And just using properties of integrals, the integral of a difference is difference of integrals, and then factoring out your constant, we get the area between two curves formula to be what you guys see right here. And that's the top, r squared minus r squared bottom, and then we factored out the 1/2. And this is also used, but that's for area between two curves now. Anyway, it's a nice proof for you guys here of this, and of course we want to see how to apply these things. And go back. We're going to start here with area under a curve between two lines that go through the origin, alpha and beta, and area is 1/2 r squared d theta. All right, so where is this? Okay, so let's say, remember, area is the integral of 1/2 r squared d theta for alpha and beta. Alpha less than or equal to theta less than or equal to beta. Okay, and these are lines, alpha and beta are lines through the pole. And what did I do this morning? So this morning here, I got a bunch of examples for you guys here, and I'm going to kind of look at what the book wants you to do. So the book is saying for a couple of these here, they want you to find the area. Bounded. So let's find the area of the region bounded. By the curve that lies in a, what they call a sector here. And so the first example I'm going to do looks like this. They're going to take the curve r equals e to the theta over 2. And let's do a nicer theta. Over I'm going to say 0 to pi. I'm going to change this on you guys. This is a little different. So it's not exactly what they gave you in your book. And I want to remark here, I'm going to give you the curves here. I'm not going to ask you to sketch them. There's not a lot of time for us to do those details. So I'll give you the curves. And this is the function. This is r equals theta over 2 over 0 to pi. Now, let me show you what that looks like. So this morning, I'm going to change this now. I'm going to say this is actually 0 to 2 pi. So if I do 0 to pi now, I believe we just spelled pi. There we go. Nice. 0 to pi here. So let me take a picture so I can write on this. Okay, so what I'll do here is I'll demonstrate to you a couple of things that theta is 0. This is theta is 0 here. Okay, here's your pole. You guys can see that a bit, right? And then we rotate that to pi. And of course, you say, isn't that just on the other side? And the answer is yes, right here. This is theta is pi. So that the area they're talking about here, ladies and gentlemen, is what you see. So this is the area that they're talking about. Now, they could have said, what about 0 to pi over 2? And maybe we should do that. This is 0 to pi. And since we're on kind of this discussion, this is kind of a nice curve. I like this curve. If they said 0 to 2, maybe pi over 2, right? Then they'll talk about that curve, that portion of the curve. So, I mean, I could go back and say to you, and I know I erased this. I mean, I changed it to pi, but the point is you got a portion of the curve. Yes, it's 0 to pi, but if they tell you find the area between 0 and pi over 2, I mean, this is what they're asking. And so maybe we should just change this question to pi over 2. It kind of looks a bit fun. I don't know. But if it's 0 to pi over 2, this is what it looks like. If it's 0 to pi, it'll look more like this. Okay, so you guys kind of understand what the idea here is. So I don't know. Maybe we'll stick with the original. Why change? People don't like change, right? And there we go. We'll go to 0 to pi, like we originally said. But you guys get the idea. The reason I wanted to emphasize that theta equals a constant is a line the other day is because you're going to use these ideas. And again, on a test, I'll give you the curves, and you just go with that, okay? So here's something that we wanted to look at, and we're done. And I guess we, save to files maybe. Okay, yeah, maybe save that. Who knows? Whatever. Just in case. Okay. We're going to keep it 0 to pi. So all you guys have to do is use your formula. And notice in your formula, right, you need an r squared. And yes, you need the constant 1/2. So what we're going to do is we're going to square r. So if we know what r is, r squared becomes e to the theta over 2 squared. Or we know r squared will be e to the, remember you multiply the powers, it's just e to the theta. It's your r squared. So the area now is going to be 0 to pi 1/2 e theta d theta. So we pull out our constant and we just integrate from 0 to 0 to pi here, e theta d theta, and you guys know what that gives you. That's just e theta. And you evaluate this from 0 to pi, and this is 1/2 e to the pi minus 1/2 e to the 0. And of course, we know e to the 0 is 1. And final answer for this area, 1/2 e to the pi minus 1/2. We could leave it that way, or we can say the area is, if we factor out the 1/2, it's e to the pi minus 1. So here you go. Here's your first area type question, ladies and gentlemen. And, that was pretty fun. Okay, remember we need to know how to integrate. And that was the first curve. So let's look at another curve, because this is all fun. We're going to look at r equals sine theta over this interval. We're going to look pi over 3 less than or equal to theta less than or equal to 2 pi over 3. Now, I might even change this, and they don't even put the word over. They'll just put a comma. So maybe we'll do that, or a semicolon. They're just saying that this is your interval here. Okay? Kirby has a good question. Um, no, Kirby, they're not going to give you those kind of things. Okay. All right. Now let's see. Here's Kirby says, if we wanted to do that, well, they're not going to give you that kind of stuff. Okay. You're first learning how to do this. So we're going to go R sine theta. Here's the curve. And go back to Desmos. And I don't think I have that one. Did I plan on that one? Let me double check my notes. Actually, I didn't plan on that one. So good. I don't want to do the odds for you. I want you guys to do the odds. So I'm going to change this one. I want to do the evens. So we have r squared is sine theta, and this is over. Well, this one's over to 0 to pi, so maybe we'll change this one. Right? Maybe we'll change that one to pi over 2. I don't know. We'll see. And I want to note to let you guys know, here's kind of a thing. R squared is going to be positive, in case you guys remembered how to graph these things. Because you're not going to have a negative r squared, because then r will be imaginary. Okay, so that goes back to trigonometry when you try to graph this. So r squared is sine theta. And so in your book, they actually write this as r is a square root of sine theta. So when we look at Desmos, I did that this morning, because even this program doesn't graph it's called a relation. And I think when we look at this today, this relation, let's try to do this one from 0 to, pi over 2 maybe. So maybe we will change that, right? But let me show you the difference. And we'll say, okay, so I don't do everything exactly the way it is. 0 to pi over 2. And here we go. Okay, so of course we need a picture of that. And we're going to take that picture. And let's see what this looks like. So we can write on this now. Now remember, we're going to take a theta is 0 here. And like we described last time, we're going to go pi over 2. And so they're talking about this area. Now, I want to give you another remark, since, that's kind of what I do. If they give you pi over 4, right? Maybe if they said pi over 4, 0 to pi over 4, well, then they're talking this. That's the area. And then you say, what if they give me, well, that's not even pi over 4. That's more like pi over 3. It's more like 30 degrees, pi over 6. If it's 0 to pi over 6, then that's kind of the area in red. So this is kind of what we do here. They're going to give you these polar curves and try to find area, between these lines through the pole. And so we'll stick with the pi over 2. And of course, if they gave you pi, and you say, what if they want this to be 0 to pi? Well, then they're talking the whole thing, right? That's the whole thing, 0 to pi. Okay. So anyway, let's go back and do the 0 to pi over 2. So we're done. We don't have to really save this. Well, let's save it just in case. So let's go through this exercise, right? So we say, okay, the area is the integral 0 to pi over 2, 1/2 r squared d theta. So, of course, you guys know you need an r squared. And the nice thing about this is that you already have an r squared. It's sine theta. So we have 1/2 r squared. So this becomes the integral of 0 pi over 2, 1/2 sine theta d theta. And I guess we could pull out our constant. 0 to pi over 2 sine theta d theta. Now the integral of sine, you guys know, isn't that minus cosine, I think? See, derivative of cosine is minus sine. Yeah. So we have 0 pi over 2 minus 1/2 cosine theta. 0 to pi over 2. So let's think about that, right? Switching to green tea, not really awake. Okay. Derivative of cosine is minus sine, so the antiderivative of sine is minus cosine. Okay. All right, let's see. We get negative 1/2 cosine pi over 2 minus a negative 1/2 cosine of 0. Okay, you guys remember that? This is f of pi over 2 minus f of 0. And doing a little bit of algebra, we end up with this positive 1/2 on the right side. That's cosine, and I'm going to keep this negative. So I'm going to switch these positions. So you guys can see this is minus the minus, and then this is still negative. So that's kind of what I did. And then we say, okay, what's cosine of 0? Let's remember cosine 0 is 1. And then what's cosine of 90 degrees? I think that's 0. So the area here is really 1/2 times 1, which is 1/2. Let's write this down. Let's do it this way. How do we do the last one? Okay, the full thing. Okay, area here is 1/2. So as you guys can see, this just becomes an integration exercise, right? All right, let's take a look at some of these next questions here. Right, so this is kind of nice. All right, let's see what we have. They actually give you in this next set, they're going to say, find the area of the shaded region. And then they give you pictures now. I'm going to give you a picture. And they give you really the curve. R is 1 plus sine theta. So here's the curve they give you, and then they shade a region. They're going to show you a picture. So let me show you the picture here and see if we can try to figure that out, right? R is 1 plus sine theta. So I went to Desmos. And of course, it's a nice cardioid. Okay. Let's take a picture so we can write on it. More screenshot. And then this is what they did. This is what they shaded. Maybe since it's green, we should shade it green too. I don't know. All right. So here's what they did in your book. And they're trying to ask you, hey, determine the area of this shaded region. What is this, right? This shaded region. Well, what you're going to need to do again is determine those lines through the origin. So you start here. Now remember, you're going counterclockwise. And that's the angle theta is pi over 2. And you say, why counterclockwise? Because that gives you an increasing theta. And when we write down intervals, notice when you say alpha less than equal to theta less than equal to beta, that's increasing theta. So that first angle is pi over 2. The second angle, you have to know what that theta is. And you say, well, what's this theta? This theta is going to be, 1 pi over 2, 2 pi over 2. That theta is pi. Now, I want to remark here like I always do. In green, this is the question. Pi over 2 to pi. So they want us to do that. Pi over 2 less than or equal to theta less than or equal to pi. And in blue, I'm going to shade something here for you guys and see if you can figure something out. Let's change that color. Here is something they can give us. What if they gave us the bottom in blue? And they're asking us again in blue here now, right? What interval is that? Because they gave us only a shaded region, they want to test us on whether we understand the concept of, theta being increasing. How do we create this integral? So in blue, remember, we're saying theta is increasing. So we could do this actually a couple of ways. Oh, I want to undo that. Okay. We can start here in blue. That's theta equals pi. So I can put it next to this. And then I rotate, remember, counterclockwise. And if I rotate this ray starting at pi counterclockwise, I'm going to the other side. And then you say to me, well, what would that be in blue? Well, that's theta is 2 pi. So if you write this as increasing theta, the blue portion is from pi, starting at pi, and then going to 2 pi. So that you guys can see how to set up some of these integrals. Remember, you want to work counterclockwise. And then you say, but wait a minute, can I work the other direction? The answer is yes. You still have to write your theta is, you can actually write this with negative angles, but you still need theta to be increasing. So you could use clockwise and make sure theta is negative. You say, what are you talking about? Well, I can start at 0. Go the other direction. And you say, well, what's the other direction? Well, this is going to be maybe negative pi, right? So I want you guys to think about, how would you write this? Well, we write negative pi less than or equal to theta. You can say less than 0. So you can say, you can call this the starting point, negative pi. And I guess you're going, sorry. You're going the other direction. Counterclockwise. There we go. We're still writing this as increasing theta. So you say start the ray at negative pi and then go to 0. And I guess it's still that increasing. So anyway, my point is you can use negative angles. And you're still going in that. You can still do it as counterclockwise direction. Because you want this portion to be increasing how you define your interval. It's just how we make these intervals. We always write it smaller, less than the variable, less than the larger value. So here's different ways we can set up if we're trying to look, again, here for that same area. These are different ways of doing this. Let me go back there so you guys can swallow that a bit. So, okay, yeah, we can use the negative angles. So maybe we'll save this one to files. And I should be naming them, but I'm not. And let's go here. Okay. And what was that again? Which was that last one? I think we're going from, what was that picture? Theta here in the picture was pi over 2 to 3 pi over 2. That's the one they gave us. So it's 90 degrees to 270. Okay. And then you say, okay, my formula is the integral pi over 2, 3 pi over 2, 1/2 r squared d theta. Now your r squared here becomes something. You say 1 plus sine theta squared. And of course, you get to use some algebra. 1 plus sine theta. 1 plus sine theta. And of course, we're going to use FOIL. 1 plus, this is going to be 2 sine theta plus sine squared theta. Okay, and so we can say the area formula will be, you can go from pi over 2, 3 pi over 2, 1 plus 2 sine theta plus sine squared theta d theta. Now, you guys remember when you integrate here, because you have a sine squared, you have to replace that with an identity. That's 1. That's cosine 2 theta, right? So replace this with an identity, and I believe for sine squared, this is subtraction. So altogether, doing the algebra here for what's under your integral, let's kind of just note that. We have 1 plus 2 sine theta. That's going to be, I'm going to distribute here, ladies and gentlemen. That's plus 1/2 minus 1/2 cosine 2 theta. And then 1 plus 1/2 gives me 3/2 plus 2 sine theta minus 1/2 cosine of 2 theta. And let's double check. Did we have the 1/2 there? No, I don't think we put the 1/2. So remember, we need the 1/2 factor. So we're going to put that 1/2 factor here. So let's not forget the 1/2 factor. So it's really under our integral here for the area from pi over 2, 3 pi over 2, 3/4 plus sine theta. We're going to distribute there. Minus 1/4 cosine 2 theta. Okay. And that's d theta. So when you integrate 3/4 theta plus sine theta. Now let me be careful here. Right? I know there's a minus sign here. Minus 1/4. Here's what I want to remark. You're going to use u sub, where u is 2 theta. So this is going to be times 1/2. And you say the derivative of sine is cosine. So derivative of sine is cosine. So the antiderivative of cosine is sine. So this would be sine here of 2 theta. So double check and be careful. And that's where theta is pi over 2. Theta will be 3 pi over 2. So if we fix this a bit, 3/4 theta sine theta should be minus 1/8 sine 2 theta. Theta is pi over 2. Theta is 3 pi over 2. Kirby, we are not doing that. We're not doing these. We're doing, if I go back, I'm doing what's in the book. It was the green area. So I want you guys to know we are doing the green portion. Oh, and thank you. I think Kirby's right. I think Marbella, you are right. That should make everything nice. Let's do that. Let's do the green portion. That looks like that was pi over 2 to pi. So good. Let's do that. Pi over 2 to pi. Thank you. It was the green. So That's going to make everything nicer. I'm going to put that in green. So when you go back and look at the video, yeah, pi over 2 to pi. That's the picture that's in the book. So let's do that, definitely. That's even better. You're right. Pi. And you say to me, well, we're doing the one in the book. And why is that even better? Well, double check. What happens when you plug all these things in, right? So when you plug this in, remember you're trying to find, this is going to be f of pi minus this f of pi over 2. They're kind of nicer to work with. Let's be careful. 3/4 pi plus sine pi minus 1/8 sine 2 pi. Now, this is the first. I have to subtract now. 3/4 pi over 2 plus sine of pi over 2 minus 1/8 sine of 2 times pi over 2. Now let's double check. And Marbella has a question here, right? All righty. Let's get rid of this. Shouldn't we have minus cosine instead of sine after integrating? Oh, let's see. Thank you. Thank you again. I guess I have to go back to the coffee. Right over here. Yes, thank you, Marbella. Good job. Derivative, this is the antiderivative, right? That's going to be minus cosine here. And so that makes this minus cosine. Thank you, people are awake today. Minus cosine. Good. And that's still going to give us a good situation, I think. So let's go back to make sure we get everything here. Yeah, let's think about that, right? The antiderivative of sine right here is minus cosine. And now it looks like we're okay, hopefully. I try to focus on that other integral. All right, so we need to know what's cosine of minus pi now. Now we have to find all these values. And cosine of minus pi, right, is -1. Hopefully I'm awake about that one. Sine of 2 pi is actually 0. Cosine pi over 2, this is 0. This is sine of actually pi, and that's also 0. So double check to see if I'm awake and you guys have all these values as well. All right, cosine is -1. Sine of 2 pi, 0. Cosine of pi over 2 is 0. It looks like the answer is going to be 3 pi over 4 minus a minus makes that +1. And then that's going to be minus a 3 pi over 8 here, right? Here's minus a minus, makes it a plus, and then that's minus 3 pi over 8. Okay. So I'm going to need to subtract here. So I need the same denominator. 6 pi over 8 plus 1 minus that 3 pi over 8. So our area looks like it's going to be 6 pi minus 3 pi. That looks like it's 3 pi over 8. And then that's +1. So here's a picture of what they want you to do with that particular kind of question. They're going to give you a shaded area and then ask you, hey, what's this area? So they just want to test to see whether you know how to write these lines to the origin. And then let's go to another interesting question. You guys may like this one here. The next one I'm looking at in our book here. The next example. They give us r equals sine 4 theta. And let's see what that looks like. So this is something we want to talk about. Here's r equals sine 4 theta. Now, what they do with this particular question, let's take a picture. What they're doing with this one, and let's find where they're going to shade here. Let's take that, and I want to change the color. Let's do purple. Here's what this looks like in the book. Now, you're going to say to me, this is a lot harder to find the angles. And the answer is, you're right. You're going to have to know a little bit about graphing way back when you graph these polar curves, and a little bit about graphing. I know that here theta is 0. That's the polar axis. And then I'm going to say something like this. There's a line going out this way. And I don't know what that theta value is. I'm not sure. If you guys remember some graphing, you have this portion here. When you graph this curve, there's a technique to graph, and I teach this in trigonometry. It's in that course. And of course, this curve is being sketched out, in two portions here. Here's my point, though. The question is, that's a pole. So the curve, when you plotted all these points and you're trying to sketch that, and you're really drawing these lines here by the techniques of sketching polar curves, you came back to a pole. So since this curve here I guess we lost our purple? No, our purple's still there. Remember what the curve was. This curve was r equals sine 4 theta. And then you say, where do I get the pole? Remember, the definition of a pole was 0 theta and any theta value. That gives you the location of your poles. So this first portion is 0. That means 0 is sine 4 theta. Now, solving this equation, we know 4 theta has to be 0. It actually has to be pi. It's 2 pi. It's all those values. In fact, this goes on forever. It's 3 pi, 4 pi. And in fact, we simply write this as n pi, if you guys remember, in general, which means theta is really n pi over 4. So the first pole happens at 0, 0. This is the first part. The second pole happens when 4 theta is pi, or theta is going to be, well, if 4 theta is pi, theta is pi over 4. So, ladies and gentlemen, this value here for the next pole will be pi over 4. So you set this equation equal to 0 here, right? R becomes 0 because that's the definition. And you can find theta. Now, you say, what about the next pole? Well, when theta is 2 pi, right, theta will be, 4 theta is 2 pi. That means theta is pi over 2. So the next pole here, ladies and gentlemen, would be when theta is pi over 2 here, just so you know. So I can find, if they even ask me, hey, take 2 of these leaves. Well, if it's 2 leaves, your theta is going to be between 0 and pi over 2. That's 2 leaves. Okay, and you can do this forever. I would just say to you, if they ask you for 2 leaves, just find the area of 1, meaning 0 to pi over 4. This is the area of 1 here. Find that area and then multiply it by, how many do we need? 8. So there's a way we can find the area of the whole thing very easily. So I'm just going to find the area. This is of 1 leaf. And again, remember this. So when we write this down, it'll be 0 to pi over 4. That's 1 leaf. But I want to show you guys how you get these values. How do you find these lines, okay? It went back to a poll, and it goes back to the instinct of graphing, really. So we're gonna save that one. Remember, theta is 0 to pi over 4. Save files. That's the last one. Yeah, I guess that's it. Whatever. I don't know where we've been saving them. But 0 to pi over 4, let's try this out. So here's kind of how we can do this, right? We know r squared then is sine squared 4 theta. So that the area for 1 leaf, 0 to pi over 4, that 1/2 r squared d theta, right, becomes 0 pi over 4 1/2 sine squared 4 theta d theta. And then you say to me, well, what do I do with the sine squared? Isn't that 1/2? Let's be careful. 1. This is now cosine of 8 theta. And that's minus again. So that's 8 theta. You say, why 8 theta? Well, you got 4 theta there, and you have to double that. 4 theta becomes 8 theta. So this area will be from 0 pi over 4. Don't forget, you already had a 1/2. That gets multiplied to another 1/2. I get 1/4. 1 minus cosine of 8 theta d theta. So that the area is 0 pi over 4, 1/4 minus 1/4 cosine of 8 theta d theta. So double check. I'm kind of getting through this here pretty good. Double check to see if we're okay. Let's integrate. 1/4 theta minus, of course, u sub. U is 8 theta. And we need the antiderivative of cosine. So the derivative of sine is cosine. So that's minus 1/4 times 1/8 sine 8 theta. So double check. All right, let's see. Do we have that okay? Derivative of sine is cosine. It's minus. Okay, we look like we're okay. 1/4 theta minus 1 over 32 sine 8 theta. 0 pi over 4. So remember, this will be f of pi over 4 minus f of 0. 1/4 pi over 4 minus 1 over 32 sine of 8 times pi over 4 minus, and this is 0 now, 1/4 times 0 minus 1 over 32 sine of 8 times 0. That's 8 times 0. And let's kind of see what's nice about this. This portion is really 0, and sine of 8 times 0 is 0. Sine of 0 is 0. And this is actually 2 pi, I believe, right? So sine of 2 pi is also 0. So double check these things. See if we're okay. So it looks like the area here is pi over 16. So double check. And I'm going to say to you guys, if you went back to that picture, this is 1 leaf. Now here's a note. Here's what you guys want to know. What if they want the area enclosed. Here's what they say: find the area that the curve encloses. So let's try to. What if they want the area enclosed by the curve? Let's write it that way. Yeah. In other words, they're saying instead of 0 to pi over 4, they're talking 0 to 2 pi. And you say, what do you mean by this? Yeah, this is going to be, let's go back here. Let's remember, pi over 16. All right, so let's take another picture. So pi over 16, right? So if they said to you, oh, we forgot the picture. We need purple again. This area is pi over 16. Now, from 0 to 2 pi, remember your pole is here. You rotate counterclockwise and you come back here. So we're really saying now this is the area enclosed by the curve. Area enclosed by the curve. Now, I'm not going to say go back and do the integral again from 0 to 2 pi. You can say, all right, integral 0 to pi 1/2 r squared d theta. You can do this all over again. But what I remarked earlier was if this is one leaf you found, you can just multiply that by 1, 2, 3, 4, 5, 6, 7, and 8, so that I can take 8 times pi over 16, and that area is going to be simply a pi over 2. So here's what I wanted to remark to people. If they ever say find the area that's enclosed by a region, it's going to be the whole thing here from 0 to 2 pi. And what will happen now is actually just find the area of, if there's some symmetry, and usually there is because this is polar, use symmetry. Find the area of one leaf and then multiply by how many leaves there are. So if there was 4 leaves, you find the area of one and then multiply the rest by 4. Now you say, can I just go from 0 to 2 pi? Yes, you can. You could do that too. Okay, 0 to 2 pi. Now let's go back here. That's a nice remark to remind people. And we have a question here. Let's see. I think we forgot to subtract the part of the integration. Subtract the part, the second part. Okay. Well, I don't think we did, but maybe you're right. Let's double check, right? I don't think we did. The second part, because theta is 0 here, right? Theta is 0. When we plug in 0 for theta, this portion is 0. And then 8 times 0 is 0. This portion is 0. Sine of 0 is 0. So I didn't forget to subtract, I don't believe, but I'm subtracting 0. The point I want to make is if this whole portion is 0, then you don't, then it's done. I mean, that's 0. It's not there. So it looks like, yeah, we forgot to subtract. I don't think we did, but it looks like we forgot, but we didn't. It's pi over 16. So anyway, here's the part I want to remark to you guys. If they said, okay, what about 0 to pi over 2? Well, then you know what? That's going to be 8 times pi over 16. And we say this is going to be really pi over 2. So that's one way we can do an area enclosed by the curve. Now, I want to try to see if we could squeeze in this example, since we're going to say, we're in the idea, what if they want the area enclosed by a curve? And you go, the whole area? Yes, the whole area. Let's give you another curve. R equals 3, 1 plus cosine theta. And they want area enclosed by the whole curve. The whole curve. And so I have this for us already. And as you guys can see here, let's try to take a picture. The area they're talking about is all of this. That's area enclosed by the whole curve. So again, remember, this is going to be 0 to 2 pi, right? We're starting here when theta is 0. We're rotating counterclockwise. So this includes this small portion. And so here's where we're at pi. You know, theta's pi counterclockwise, and then we keep going, and we get this is the top portion from 0. Theta is 0 to pi is the top portion, and then we include the bottom, so we continue from pi to 2 pi. So this is an area enclosed by the curve, the whole curve. So it's a cardioid. We're going to find the area of a cardioid. So here's what this is. Area will be the integral 0 to 2 pi. That's enclosing the whole curve. 1/2 r squared d theta. Now, this is replace. R, remember, is going to be 3, 1 plus cosine theta. So when we square this, it's 9, 1 plus cosine theta squared. So we're going to try to square this. And of course, this means we're going to have to use FOIL again from algebra. So we get 9 here. 1 plus 2 cosine theta plus cosine squared theta. And you can say that's 9 plus 18 cosine theta plus 9 cosine squared theta. And you guys remember, you're going to have to integrate. So I need an identity here. That's 1/2, 1 cosine 2 theta. But because it's, remember, this is going to be plus. That's the identity for cosine squared, right? Because we're going to have to integrate. Now, I did it now here because I want to multiply this by 9. So let's do some more algebra. You get 9 plus 18 cosine theta, really plus 9 halves now, 1 plus cosine of 2 theta. You could distribute 9 plus 18 cosine theta plus 9 halves plus 9 halves cosine 2 theta. Multiply by 2, divide by 2. 18 halves plus 18 cosine theta plus 9 halves plus 9 halves cosine of that 2 theta. So 9 and 18, I believe that's 27. So let's write it this way. The area is, let's make sure we have that factor of 1/2. Did we include the factor of 1/2 at any time? No, we didn't. So let's include the factor of 1/2, ladies and gentlemen. We just did the algebra. So what that's going to give us here is, let's do this here instead. Let's write down, let's combine a term. This is really 27 halves plus 18 cosine theta plus 9 halves cosine of that 2 theta let's not forget the factor of 1/2. Okay. And I'm going to distribute, and we're going to find what this integral is going to be. So area will be 0, 2 pi. Looks like it's 27/4 plus 9 cosine theta plus 9/4 cosine 2 theta. That's d theta. And that looks like it's that looks like it's what we get here. I mean, this is in our book. Anyway, just double checking. Okay, absolutely. It looks like we're good. Just double checking everything. Now I'm going to say to you guys, well, what's our time like? We got a few minutes. We got a few minutes to try to integrate this. Let's try to integrate. Yeah, I think we got a few minutes here. 27/4 theta. Derivative of sine is cosine plus 9 sine theta. Okay, again, u sub. So I'm going to say, let's be careful. Derivative of sine is cosine. So 9/4 times 1/2 sine 2 theta. Let me double check. Okay, derivative of sine is cosine. So it looks like we're good. So we have 27/4 theta plus 9 sine theta plus 9/8 sine 2 theta from 0 to 2 pi. Okay, so let's try to double check here. We're going to get f of 2 pi here minus f of 0. So here's what this is going to give us. 27/4 times 2 pi plus 9 sine 2 pi plus 9/8 sine, really, 4 pi. And then we're going to subtract. We're going to subtract a bunch of zeros. 27/4 times 0. 9 sine is 0. 9/8 sine, and that's really 2 times 0. That's not 20. So we got a bunch of, this is 0 here. It's gone. This is 0. It's gone. 0. That's gone. So it's going to look like we forgot to subtract, but we didn't. Let's continue. This is 0. This is 0 because 2 pi and 4 pi for sine. So that's kind of nice. Okay, let's see what this leaves us with. Looks like our area now is going to be, if we simplify over here, where's our red? Looks like the area becomes 27/2 pi. Yeah. All righty. 27.5 pi. Okay, so this is what we get here for this question. And checking in back of the book for this, we are correct. So we have another question here. Are we having a minus 9 cosine? Not quite sure where you're getting at, but again, I checked in back of the book. This is the correct answer. So double check your work. Double check your work. We're good. So this is how we find the area of an enclosed curve. Now, I think I wanted to do something like this, the same thing. Here's what I wanted to do. Maybe you guys can try this. Area of, Well, let's just, I'll just stop it right there. This is good. This section is 11.4. And what I'm going to do for you guys for now is I'm going to ask you to do 1 to 14 all in 11.4. And of course, like I said, you guys should be expecting additional examples for the stuff we did yesterday and the stuff we did today. Okay? Um, but double check. And no, we actually, I think I did it correct. So double check your work. Okay? Everything that I see on my end is consistent. Right? It's consistent with the answers or the answer in the book. So double check what you guys have. But I want you guys to work on this area here, 11.4 to 1 to 14 all. And like I mentioned, yeah, we're going to give you more examples of these things because they're great and they're fun. And things we did yesterday, like arc length, we want to give you guys that. Additional examples and additional examples of some of these area questions. And then that's that. So, ladies and gentlemen, I hope you enjoyed area for polar curves. Um, I'm working on grading your tests, so you guys should be there too. Here's the deal here. What's the question here? We go, okay. Can we use our calculators to graph as shortcut during exams? Like, no, I will be giving you, Marbella, it's a good question you have. I will be giving you, because calculators do the work, I will be giving you the curves. In other words, all the curves that are on your test and final and stuff like that, I put them on the test sheet so you don't have to use a calculator to graph them. Okay, so no, on an exam, no, you're not using a graphing calculator. I'm using this to demonstrate the curve for sake of time. But on an exam, you get the curves. So I'll just show you the curves here. That'll be in question like 1. Here's the curve. Find the area it encloses. You have to do the algebra and the integration and use the right formula. So anyway, anybody have any other questions briefly here since we're on the topic? That's a very good question. Okay, thank you, Kirby. You're so welcome. I hope you guys have a great day. I hope you guys, you know what, stay safe. Thank you, Sheila. Thank you, guys. This is nice, good fun. You guys are learning. Thank you, Sam. You guys are learning some good stuff. So take care, stay safe, and I'll see you guys tomorrow. Thank you so much. Thank you, Marbella. You're a great help. Thank you.